All right, we are back from break, and we had been just finishing up this problem. This is another really good, thorough problem, just a couple of items that could be included to make it a little more clear that the tangent of the angle phi is equal to y divided by x. So that's where that angle information is coming from. Again, any questions, stop by office hours and let's get your questions looked at. Now, it turns out that any vector, v, can be written in terms of its components. We want to be able to write that in kind of a vector notation. Now, what I've been doing for that is, I've been doing this. So if there's a vector, I write this matrix, this column matrix or vector is actually what they are called. And then I've been writing x, y, and if needed, a third level would be z. So that's the way I've been writing to show what the components are. The textbook uses a different approach. And it's a good approach. It's one that gets used. This is also a commonly used approach. And that is to say that the vector consists of vx, vy, and vz. The vx is in the x direction. Now, another notation that gets used is little e gets used to represent directions. But the book is using I hat, and this is actually, they're both common. The vy, for that we use j as a vector showing direction, and then k shows direction in the z. And so you're going to see vectors written this way in the textbook, and from time to time I'll use that too. What the I, j, and k are what we call unit vectors. Since the I, j, and k, we're not using those to keep track of distances. We're only using those to keep track of direction. So I think this is pretty clever, mathematics to be working in terms of saying that I've got this much of the vector in that direction. Now, to make that work, what we do is we say that the vectors I, j, and k have a magnitude of 1. And that's why they're called unit vectors. They're called unit vectors because they only have a magnitude of 1. They don't affect the magnitude of the overall component. So the component's magnitudes are written as vx, vy, and vz. Maybe this is 10 meters, and this is 12 meters, and this is negative 17 meters. The I, j, and k are each 1, so multiplying by 1 doesn't affect those magnitudes, but it does add on, it provides the directional information. So it's just another way to write the vectors. Now we're going to be taking these vectors and we're going to be looking at more detailed kinematics. So remember, the chapter here is, the intention of the chapter is to be able to work in three dimensions. So this is a very general idea of how do we get, three-dimensionally, how do we get from point 1 to point 2? Let's say that there is some path that's being followed. And I know these diagrams always frightened me in my math classes and my physics classes because I thought, oh my gosh, what function could that possibly be? It turns out we seldom work in terms of functions that are this complicated. This is just a general idea to try to think of how these vectors work. So what we could do is we could define displacement 1 as giving us the location of where the object is at a particular time. So at time 1, the object was right here, and then it traveled, and at a later time, it was at this different location, and for that I can use a different displacement vector. Now the displacement vectors R1 and C, they switched to R. See, it was right after the break. They stopped using big D, and after the break they're using little r. So these are, what we can do is we can say that the actual path that's being followed, it is not displacement vector 1 or displacement vector 2. It's really approximated by delta displacement. So it's the difference between displacement vector 1 and displacement 2 that is approximating the path between P1 and P2. Actually, this is the displacement between those points. Now, as we do this at smaller and smaller time intervals, okay, so let's not wait so long. Let's do a displacement measurement here and then a displacement here, the delta R is going to become better and better representation of the path that we're actually following. So if we do these over very, very short time intervals and we keep measuring the displacement vectors, what we can say is that taking that displacement vector, the delta displacement, and dividing it by a time interval is giving us a better and better measurement of the velocity vector. The velocity vector is going to be in the direction of delta r. This is the actual displacement. So if we want to find out what the velocity is and what its direction is, the direction of velocity will be in the direction of delta displacement. Now, as we do shorter and shorter time intervals, that delta displacement becomes an infinitesimal. It becomes dr, and the delta t, the time interval, becomes an infinitesimal time interval dt, where, if you guys remember from calculus, infinitesimal is meaning in the limit of making it as small as possible. That ratio of displacement to time will give us the velocity. Now, this is a little weird because what does this even mean? And what a displacement vector consists of is a little bit of motion in the x and a little bit of motion in the y. It consists of a dx and a dy. So this is showing where the vector, the velocity vector, is located. Now we can do the same thing for acceleration. What we can do is, here we are at point 1, here we are at point 2. Here is the displacement vector representing the location of point 1. We didn't actually travel that displacement. It's a displacement from the origin. And then at a later time, we're using displacement vector 2 to show where we are later. The actual path followed was this. Now what we can say is, well, it turns out from the previous analysis, the velocity vector is always tangent to the path that we're following. You know, if I'm wandering around curvy kind of path here, at any instant, if I take a line that's tangent to my path, that's going to give me the instantaneous direction of velocity. And this over here, I don't think they got it right. I don't think that's tangent. I think it's tipped a little bit more. What do you guys think? See, that doesn't really line. It kind of crosses here. I think that green arrow needs to be shifted a little bit downwards. Anyway, this is the velocity vector here. Here's the velocity vector at a later time. We can do a little bit of vector magic here and say that what we do is we pick up vector 1, we pick up vector 2, we bring them together, and we analyze them on a vector diagram. And the vector diagram is telling me that if I take V1 and draw that out, see, I parallel transport them. So I keep the magnitude and the angle and draw it. Same thing here. This one's tipped, so I've got to bring that down tipped. So vector here, vector here. The delta V, the difference in the velocities between when the velocity looked like this and when the velocity looked like this, is actually this direction. So that's kind of interesting. We've slowed down and we have redirected the velocity, and the net effect here is to have the delta V back in that direction. Well, we can say then that that's the direction of acceleration. Acceleration is going to be in the direction of delta V vector. So if we look at the velocity vector and how it's varying from point 1 to point 2, and then take those differences, divide them by a time interval, that will give us the acceleration. So the acceleration components can be determined by taking time derivative of the velocity components. So, and we should have a diagram outlining all that. Here it is. When we say that the velocity vector comes from taking time derivatives of the displacement vectors, what that's really saying is in the x, y, and z directions individually, we're taking dx dt, dy divided by dt, and dz divided by dt. For the acceleration, when we write this as a vector form, there's really three things going on. there's dvx dt, dvy dt, and dvz dt, each in its own direction, I, j, k, which represents the x, y, and z directions. So that's what these, all this vector notation is keeping track of. Okay, so right up to here, everything is completely general. We have a displacement vector that we're representing as r. We take derivatives of all the components individually to get the components of velocity. This right here is vx. This right here is vy, and this expression is vz. Now we take those and take one more time derivative. Again, we take the infinitesimal and divide by dt, and that gives us the components of acceleration. So dvx dt is ax, dvy dt is ay, dvz dt is a z component. That's how it works. Now what we can do then is we can go, okay, very good. What we can do is go back to chapter 2. Remember back in chapter 2 we said, let's limit ourselves to accelerations that are constant and see what kind of examples we can come up with. And so I think that's what we're going to do now, is we're going to come back and say, what would happen if I had an object where its accelerations are going to be constant? And what would happen then is, looking back at those formulas we had before, we're going to have a set of formulas in the x direction. And I hope at this point you're looking at it and going, well, yeah, these are the formulas that we derived back in chapter 2. And now what we do is we're writing them down exclusively in the x direction, what's going on in the x direction. And then we just duplicate them, only this time they have subscripts for the y direction. And, you know, you guys should be thinking, and we could do this for the z also. We've only shown two of the components, two sets of the directions, x and y. So this is the x motion that we talked about, the x displacements, the x velocities, the x accelerations. These are the components in the y direction, y components of displacement, velocity, and acceleration. And what we have to do now is mash them up. What variable do they share that we could make use of? And notice, the only way to connect all of the y information and all of the x information is using time. So what happens is, I find out at a certain time where am I in the x direction, and then I can transfer that time back over to the other side and find out how fast I'm going in the y. And so time is going to be the only way we can switch back and forth. Now remember, this is assuming that the accelerations are constant. So it's assuming that the ax is constant and the ay is constant. Now there's going to be plenty of situations where we're not going to have accelerations going on both in the x and the y. With gravitational forces, for example, if I'm looking at the gravitational effects, the ax is 0. You know, gravity is not acting in a horizontal direction, so all of the ax terms will drop out. But the accelerations will be present in the y if I'm looking at gravity. So let's see what we've got here. We're going to be looking at what we call projectile motion. So we launched something, we took an object, a ball, and we let it bounce a few times here. See those really pretty parabolas? That's because of gravity. What's happening here is the x motion just stays constant. There's no force to disrupt that. And if there's no forces acting on the object, then its tendency is just to maintain a steady x direction. But in the y direction, there is constantly a gravitational force coming from the gravitational field of the Earth, exerting a force and creating an acceleration downwards. So this is an example of acceleration in the x is 0, acceleration in the y is equal to g. It's equal to 9.80 meters per second squared. Now over short distances, we can treat these as parabolas. So here's projectile motion. here's where we're headed. Let's say that something rolls off the edge of a table, and it's got x velocity to it at that time. The x velocity is unaffected by the gravitational field of the Earth. And so at each point along that parabola, the x value remains constant. But when we rolled off the table, initially, there was no velocity in the y direction. But gravity, little by little, increased that downward velocity. So at first we have no component of velocity in the y. Here we have a little bit of velocity in the y. Here we have more and more and more. And the result is to tip the combined velocity effect, and that's what creates the parabolic motion that we see in projectile motion. Now, if we had just dropped something, instead of rolling it off, or we gave it an initial velocity right here, if we had just dropped it, notice that as time goes by, it would have fallen at the same rate. The rate at which something is dropping in the y direction is independent of its x position and its x velocity. And so if we rolled one object off the table, and right as that goes off the table, we drop another object, they're going to fall side by side. They're going to be picking up speed as they drop, but the vertical fall here will match the vertical fall of the other object. The only thing that's happening over here differently is that there's a steady motion in the x direction. That remains constant. So let's see what the mathematics is going to look like then for this. This is just more of the same, showing how this works. Now here's a little different. I guess before we get right to the equations, what if we launch something instead from the ground so that it has an initial x velocity in and an initial y velocity? Now, again, you could put these vectors on everything. I prefer not putting the vector signs on the components, although strictly speaking, I guess they are vectors on their own. But there really isn't anything going in that direction. The direction something is traveling is this tangent line to the path. So I prefer using that as the velocity and just calling that a component Vy and component Vx. So the acceleration happening here is due to Earth's gravitational field. Now Earth's gravitational field is a vector, and it points downwards. So it points towards the center of the Earth. And so we can represent the acceleration here as being in the j direction with a magnitude of g and in the downwards direction. So assuming up is positive and down is negative, that we're using that coordinate system, that's how the acceleration is going to be represented. And you can see when we launch it, same argument, that in the x direction, the motion, the Vx component remains constant, whereas the y component gets smaller and smaller. At the top, the y component's gone. And then we see that it reappears in the negative direction and then increases as it picks up speed and drops to the surface. Okay, so here are those modified formulas. This is kind of what we hinted at before, is for the horizontal motion, we are going to set the acceleration equal to 0, and Vx becomes a constant. So the velocity is constant in the x direction. Now in the vertical direction, we are going to have an acceleration, and that's going to be given by negative g, and that's going to be a constant. So here we have constant acceleration of negative g. There we have constant, in the x direction, constant velocity Vx. And so we keep the three acceleration formulas here. We've taken out the a's and replaced them with negative g. Negative g, negative g, negative g. Over here, we've just dropped out the acceleration terms. Okay, so here are the projectile motion questions and the way that we are going to solve these. So what we want to do is, okay, you guys got to remind me, make sure I'm reading the problem carefully and not just skimming over. Make sure you're clear about which objects are being analyzed. Draw diagrams, pick a coordinate system, and for a set of calculations, you have to stay with the same coordinate system. During a problem, you can break it up into pieces You can set up one coordinate system to answer one question. Maybe you set up a different coordinate system to answer a different question. That's allowed. But while you're in the process of answering one question, you got to stick with a consistent coordinate system. Decide on time intervals. Okay, examine the x and y motion separately. And again, a reminder, x and y motions are going to be related by t. T is the way we get back and forth between questions about what's going on in the x and what's going on in the y. List the known and unknown quantities. Remember Vx, that's a lot of steps here. Vy is equal to 0 at the top. That's a good thing to remember. You know, plan how you're going to try and solve the problem. And then if that doesn't pan out, go back and think, you know, and course correct and come back and maybe try something a little different. All right, let's look at some examples with projectile motion. So we have a stunt motorcycle driver who's signed the contract, is going to drive off this cliff, and the contract says that you need to drive off fast enough so that you land 90 meters away, and it's going to be landing at an really high speed. It doesn't look good. Anyway, there's a movie crew with some cameras out over here. They're going to be keeping track of the landing and the whole stunt. So the movie stunt's going to drive off a 50-meter high cliff. How fast should the motorcyclist be moving to make sure that they travel the 90 meters? So they kind of got a coordinate system set up. What they've chosen for a coordinate system is the origins right here. That's fine. You know, you could have imagined a coordinate system right here. That probably would have worked well. But this is fine, and it says that in the y direction, we are going to be traveling in the negative y direction. And the landing site is at x equals 90, y equals negative 50. So write that down. Write that down in terms of solving the problem. So here we go. D is equal to 90, h is equal to 50. I changed their coordinate system. So see, I did use this as the origin. So I said that the motorcyclist is starting out at a height of 50 meters and is traveling 90 meters over to, and I introduced point A and point B, and my motorcycle really looks like a bicycle. No, my motorcycles always look like bicycles. Okay, so x naught is going, oh no. Oh yes. So x naught is 0, y naught is h. So the coordinate system is, origin is down in that corner. Here x is equal to 0, but y is equal to 50. That's what I've got written. The distance that we travel in the x direction, now this is, d is in the x direction, is going to be given by v naught times t, and v naught's going to stay constant. I've got this velocity at which I'm coming off the cliff, and as time goes by, I'm going to be traveling horizontally at a constant velocity. Now, the formulas here for x motion is going to be x naught plus v naught times t. For y motion, for displacements in the y, is y naught minus 1/2 gt squared. The v naught, there's a v naught in the x direction, but there's not a v naught in the y direction. So I dropped that out of my formula. And then over here, what that became is, well then, h is equal to 1/2 gt, substituting these numbers into that formula, and substituting these in also. So I'm taking all this stuff, I guess I'm doing it algebraically, take these guys, plug into those formulas, and I'm getting this and this. This is my vertical motion, this is my horizontal motion. And what's happening here is, for this formula, I don't know what the speed is, I do know the distance, but I don't know the time. There's not enough information to solve. So I'm going to come down and try this formula instead, and it turns out with the accelerated formula, the gravitational formula, I can solve that one. And I can solve that because I know how high I'm starting from, and I know the value of Earth's gravitational field. And so Earth's gravitational field is at 9.8 meters per second squared. And the height I start from is 50, and that's enough information to say that it's going to take 3.19 seconds to drop 50 meters. Now, that would have happened if the motorcycle was just pushed off the cliff. Let's say instead of driving off at some high speed, we just push it off, fall straight down. It's still going to take 3.19 seconds. So the speed that the motorcyclist sets up for the stunt is going to not change the fall time. It's still going to be 3.19, and that's because the motorcycle is traveling horizontally at the time they come off the cliff. So all of the initial velocity is just in the x direction. So 3.19 seconds. Once I know the time information, then I can go back to the x direction and solve for v naught. V naught is going to be the distance divided by that time. It says the motorcyclist needs to be going 28 meters per second. So that's going to be 60 miles an hour, something like that. Now, we haven't taken air resistance into account, and the motorcyclist had better include that. So the motorcyclist had really better include that information, okay? Or they're going to be in serious, serious trouble. All right, here's a football being kicked. It's kind of the same, well, it's not the same thing because this time we've got an upwards initial velocity. So that's going to complicate things. Before, the problem was not so difficult because we came off the cliff horizontally. But now that initial launch is happening from the ground, and then the ball's going to come right back down to the ground. So let's see what this leads to. Now remember, I'm going to go and label some points. A is my starting point. And at the starting point I have a velocity of 20 meters per second. And I have an angle, the initial angle of that velocity is 37. So I've got the initial velocity and I've got the initial angle that I'm working from. And I'm going to say that I'm starting right at the origin. That'll simplify my equations. So given this information, what we can say then is that x is equal to v naught x times t. Now v naught x, if I do vector resolution, if I divide the v naught into components, I'm going to get a v naught cosine theta in the x direction, and I'm going to get a v naught sine theta in the y direction. So I can write these either way. I can write them as v naught x and v naught y, or I can write them as v naught cosine theta and v naught sine theta. Depending on what information is given, you know, one method may make the problem easier. Just be aware you've got that flexibility to switch back and forth. So this is my formula for constant forward motion, and these are my formulas for displacement and velocity in the y direction. Now in part A, they're asking about point B, and they're asking about the time. How much time is it going to take? And we know at point B the y velocity has gone to 0. So I can come down to my y velocity formula and set that whole thing equal to 0. Well, if Vy is equal to 0, it says that V naught sine equals gt. So at the top, I can write down V naught sine theta equals gt. Now I'm using the sine here because they gave me the angle and they gave me V naught. And so V naught sine theta is 20 meters per second, sine of 37, and then I just have to divide through by g, and that'll tell me the time. So this, you know, this football gets kicked. There's no air resistance. Once again, we're on the moon. There's no atmosphere. And it's going to take 1.23 seconds to reach that height, given what the initial velocity was in the y direction. So see what's happening here is the initial velocity in the y, along with knowing the gravitational field, that's enough information to determine how much time it will take until it stops going up. Now what's happening here is the football didn't get kicked exclusively in the vertical direction. There's also horizontal motion going on. Once I know how much time it takes to get to the top, I can use that to determine how far down range I will be. Now, here we did get the time. We came back. We came back and used, I want to see where we've written the other formula here. So this is one of my velocity formulas, but I guess I did use that. Okay, so I was thinking there's a third formula for constant acceleration which would have come in handy here also. We could have used that one. But I actually used this formula to get the time, and then I moved on to this formula to get the location. They wanted to know how high we are going to be at point B. So for that, I moved on to the equation listed right here. I put the times in, and I put in the values of g, and ended up with 7.39 meters. That's the maximum height. What I wanted to point out here is that instead of using kind of that the two equations, I could have come back. I didn't write this one down. So just to be thorough here, I could have used this equation instead, and that I could have calculated the height in one step instead of in two. Now it does turn out in this problem, knowing the height is helpful. So I'm going to be able to use that 1.23, or maybe they ask, I need to read the problem more carefully. Nah, it just says maximum height. So it did not ask about the time. Oh, but part B asks about the time. Now, for the time, there's a couple different approaches we could use here. What we could say is y naught is equal to 0, and then at point C, when it hits the ground, it's back at 0 again. So I'm thinking in terms of point C, and y is equal to 0, and y naught was equal to 0. Those two drop out. So what happens then, if I come back to this equation, what happens is that y is equal to 0. That part drops out, and that leaves us with 1/2 gt squared will be equal to v naught sine theta times t. I can factor out one of the t's, and it tells us that tc is equal to 2 times v naught sine theta over g. Now we can plug numbers in. That gives us 2.46 seconds. Notice that the total time is twice the time it took to get to point B. And that's because there's a symmetry here. We're landing at the same elevation that we started off with. And since we're ignoring air resistance, what will happen is, whatever happens to this on the way up in terms of velocities and displacements will happen again in reverse order on the way down. And that tells us that it's going to take the same amount of time from going from point A to B as it takes from B to come back to the same elevation at point C. So we could have just multiplied by 2. We could have taken this number, multiplied by 2. That would have worked. Algebraically, we showed that. So the time it took here was 2 v naught sine theta over g. At point B, it was just v naught sine theta over g. So we do have that extra factor of 2 in there that tells us it's going to take twice as much time. All right, so another good example there. Let's ask some more questions. What's the total distance traveled? To find out how far we've traveled, we could start looking in the x direction and say at point C, we will have been traveling for 2.46 seconds. And we've been traveling at a speed of 20 meters per second times the cosine of 37. Total distance should be 39.2 meters. That's a pretty good kick. 40-something yards, 39.2 meters. That's not actually the one. That's not. I wanted to go back and look at the diagram. Where is it? There it is. And so what's happening is we've got this constant velocity in the x direction. And if we take the 2.46 seconds, it will tell us how far downrange we'll be at that time. Now it turns out the ball has come back down at that point. How far will we be when the ball has gotten to point B? How far downrange is it? And it's half the distance. So it's just traveling at that constant speed. And then, oh, that's what they ask about. Okay. Oh no, they're asking me about velocity components. So when we get to point B, the velocity in the x direction has not changed. So let's be very clear. Vx, v naught cosine theta, 16 meters per second, that's been steady. You know, the x motion has stayed, x velocity component has been constant the whole time. In the y direction, when we're at the top, there is no velocity. And then what about the acceleration? Well, there's no acceleration in the x direction, but in the y direction, there is an acceleration of negative g because of the Earth's gravitational field. And we're going to write that as minus 9.8. Now they're asking what was the acceleration at the top. The acceleration was constant the whole time. So these acceleration values apply throughout the entire path that the object traveled. All right, here's a conceptual problem. What happens? A child is sitting upright in a wagon. Did I mention this is a really good problem to look at? So make sure you're good on these projectile motion problems. This is a good one because you've got motion goes up, comes back down. We can see how far it goes down range. A lot of good stuff going on there. Here's a conceptual problem. Here is a child in this wagon. And the wagon is just sitting there, and they throw the ball up and back. This is in the reference frame of the wagon. But now let's stand back and say, what happens if the wagon actually is in motion? The person in the wagon is kind of unaware. So they don't have to be in a wagon. They could be in a BART train. They could be in a jet plane going, 800 kilometers per hour, and they could be throwing the ball up, catching it, throwing the ball up, catching it. As long as they're in a reference frame where they're moving at a constant velocity, everything we've talked about works the same way within that reference frame. So they could be throwing the ball up and having it come back down. Meanwhile, someone standing outside watching the BART train go by or watching the plane sees the ball traveling in a parabola. So within the reference frame, the person's just throwing the ball up and down, catching it, but standing back and saying, oh, but they're in a moving reference frame at a constant velocity, what they're going to see is the ball follows this parabola and the person catches it. So they throw it up, catch, throw it up, catch, okay? All right, now there's air, they ask about that. If air resistance is neglected, so we're neglecting air resistance, and if air resistance is left out, what would happen, what would air resistance correspond to? And in this reference frame, air resistance would be like a wind coming from this direction, right? The air, not only is the ground going by for this person, but the air is going by, and that would blow the object back if there were air resistance going on. So it wouldn't land right where the person is. In this problem, what we want to do is come up with what's called the range formula. Now the range, and I'm using big R for this, so the range is this. Now we already solved this in the last problem. We went through and we looked at the trajectories and we asked how, if I launch at a certain speed and a certain angle, how far downrange is this going to land? And so that's what we're after here. There's something about Napoleon's see, I don't read the problems carefully. That's because the problems are written too long here. Anyway, we are launching an object. Apparently it's some cannonballs coming out of the cannons. They're coming out at 60 meters per second. That's really fast. We're going to neglect air resistance. What angle should they launch these at in order to hit a target 320 meters away? These cannons fire a pretty long distance here. This is kind of high tech. So same picture as before. What we're going to do is we're going to set up the formulas. The distance downrange, that's what we want, is the range formula. I'm calling it little d instead of big R. I think the big R is kind of overdoing it. Let's just say d is range. And the speed here is v naught cosine theta for some amount of time. Now, the time is going to be determined by looking in the y direction. Remember, it's the gravitational field. It's the gravitational acceleration. That's going to determine how much time we're going to be in the air. If gravity is really strong, the cannonball is not going to be in the air that long. Now, what we can do is we can adjust the angle. If I adjust the angle lower, I'm going to have more forward velocity, but I'm not going to be in the air as long. So I got to find that balance between forward motion and hang time. If I launch directly vertical, I'm going to get the most hang time. I'm going to be in the air for the longest amount of time, but the ball is just going to come straight back down, which doesn't sound like a good idea. So anyway, what we can do is we can take this formula that tells us how far we've gone downrange, and then use our formulas in the y direction to find out how much time, and we derived this in the earlier example. 2 v naught sine theta over g, plug that in for the amount of time, and here it is. Here is the range. The range will be given by 2, that came from there. V naught gives v naught squared. Sine theta, cosine theta, I get a factor of each, and then g. So the sine theta factor and the cosine theta factor, the cosine theta factor says if I go at lower angles, I'll get better forward velocity, but the sine factor is saying, wait, we've got to get some hang time in the air. The longer we're in the air, the farther we can go. So it's a compromise between sine and cosine. Now if I take a sine, multiply by a cosine, it turns out the largest value I can get for that product is at 45 degrees, and we can show that. We can actually use a trig identity. So I don't know if you remember back to your trig classes learning all these identities, but this is one that shows up at a pretty good frequency. Whenever we have a sine times a cosine of an angle, sine times cosine with a factor of 2 is equal to the sine of 2 theta. So we can rewrite that range formula in a simpler manner. So now I just need, I just put the angle into one part of the formula. Let's see what this formula is telling us. So what I did is I took that very formula, see that formula right there, the one that says range formula, and I plotted that d as a function of theta. And what you end up with, again, it's a parabola, but it's a different parabola from before. This is I'm sorry, it's not a parabola, it's a sine function. It's a sine function, it's actually the sine of 2 theta. So the sine of 2 theta would look like this. The sine of 2 theta, when theta is equal to 0, that would be 0. When theta is 45, 2 theta is 90. And so that would be where the sine would peak. And then when theta is 90, 2 theta would be 180, and that would give us the sine of 180 would be 0. So this is a sine function, and it says that the maximum value, the maximum distance that this cannon can launch, the maximum downrange distance, occurs at 45 degrees. That's when the sine 2 theta reaches its highest value. And that maximum value then would be v naught squared over g. So there's not much we can do about the gravitational field of the Earth, but we can extend the range by firing at a higher velocity. And so d max is going to be v naught squared over g. Now, there are some things we have to consider then. What happens if the distance they're asking us for is greater than d max? If it's greater than v naught squared over g, there's no way the cannons can hit that target. It's just too far away. Now, if d is exactly equal to v naught squared over g, if the distance they gave us equals v naught squared over g, then we can hit the target, but we've got to set the cannons at 45 degrees. If the distance we're trying to hit is within our range, this is our range, v naught squared over g, then there's going to be 2 possible solutions. There's going to be one solution where we fire at a lower angle, and there's going to be another solution where we fire at a higher angle, and they're going to be evenly spaced around the angle of 45. So we're going to use that approach. The sine of 2 theta then needs to be equal to the target we're trying to hit is at 320 meters. Earth's gravitational field is 9.80 meters per second squared. And the v naught squared is going to be the 60 meters per second, and we square it. Now, when I solve all that, the sine of 2 theta turns out to be 0.871. So it says, yeah, we're fine. There is a solution for this. And when we solve for theta, the angle we come up with is 30 degrees. So we actually can set the cannons at 30 degrees and we'll be able to hit the target. But remember, there was a second solution, and they are symmetrically placed on our graph that we've drawn. So if this is 30.3 degrees, there is also a solution by starting at 90 and subtracting 30.3. And that's what we've done for the second solution. Now, I went back and calculated how much time each of those possibilities would result in. And so here's the diagram. At 45 degrees, we never calculated. We should go back and determine what our maximum distance was. That would have been at 45 degrees. Now, 30 degrees is going to get us there sooner. So if we're in a hurry, if we want to hit the target right away, go with the 30.3 degrees. The 60 degrees is going to give us a longer hang time, not as much forward speed. It's going to result in the same range. It's going to hit the same location. So that diagram is showing what those two solutions look like. And the first one, the time is 6.18 seconds. The second takes, 4.5 seconds longer. So if you're in a hurry, use the 30 degrees. If you're filming a movie, an epic film where you want the cannonball to be in the air for a really long time, use the 60 degree, the 59.7 degree angle. Okay, so that's another good problem. Take a look. Is there an easy? Are the numbers easy enough that we could? This is our maximum range. I was just curious. We launched at 60 meters per second, right? So that would be 60 squared, 3,600. This is about 10. The maximum range should be like 320 meters, something like that. What distance did we launch for? 300 and what was this again? 360. So the maximum range is probably 350, 360, and we're trying to hit a target at 320. You could take a look at that and see what that works out to be. All right, here are examples of those really, really pretty parabolas. Here are some fountains with water being launched at an angle, and they make these really pretty parabolic paths. Here are these sparks being generated by, I don't know if this is metal sanding or something, so these little bits of metal arcs, little bits of metal are following these parabolas, and fireworks. So some really pretty pictures with, with that motion. So here's kind of our last topic. I think we're going to run a little bit over. Sorry about that. I think we got another 5 minutes or so. We're not quite at time yet, so we got a couple minutes. We may still run over a bit. We want to take a look at relative velocity. So let's look at a couple of examples with this. I think we're going to be fine here. So here is a river, and the river is flowing in this direction, and the river is flowing with this velocity, and this velocity is labeled as water with respect to the shore. So the water is flowing past the shore, which is the rest of the planet. The water is running past the shore at some velocity. And so that's listed as VWS, and it's in this direction. Now, there's a boat, and the boat wants to travel across the river. It wants to land at a location directly across. There's a beach area, or there's a pier. I don't see it, but there's a landing location right across here, and for that reason they want to go straight across. And then they want to come straight back. Maybe that's it. They want to go straight across because they want to be able to come straight back. They don't want to get carried too far downstream. If they get carried too far downstream, it's going to be harder to get back to the original location. So what they're going to do is, now their boat, all by itself in water, is able to travel at a speed of, oh sorry, this is the one. So here is the speed with respect to the water. Here is the boat with respect to the water. They're going to angle their boat, headed a little bit upstream. Now notice, when they do this, they're going to have a component that's going upstream, against the current. That's to maintain their position within the water. And then they're going to have a component that is carrying them to the other side. So this velocity of the boat is going to need to have a component that offsets the speed of the current. So they need to tip the boat enough so that this component offsets this, and then the boat with respect to the shore will be the y component in our diagram. Now in vector notation, we can just write that as the summation of two vectors. So, and that's how they've written it here. So let's take a look at the diagrams and see what this is. So here's the example. They've given us some numbers now. A boat speed in the water is 1.85. So this is the 1.85 meters per second. The water, the river current, has a speed of 1.2. So you can see what we're setting up here. It's a right triangle. So the hypotenuse is going to be 1.85, and the one of the sides, the side representing the velocity of the water, is going to be 1.2. And there it is. There's the triangle that they gave us. Here is point B that we want to get to on the opposite shore, directly across. And so the hypotenuse is the speed of the boat with respect to the water. And then meanwhile, the water is carrying everything downstream, and the combined effect should take us directly across. So I'm taking the sine of the angle. I want that angle right there. The sine will give me the opposite over hypotenuse. I put those numbers in, and it says tip the boat 40 degrees. So the boat doesn't have that much of a margin to work with, right? The current's at 1.2, and the boat's, you know, the speed of the boat's 1.85. So they have to tip this at a pretty large angle. Now, what does that say? The speed will be for the boat making its way across, and the speed of the boat with respect to the shore, the BS velocity, is VBW squared. So we're using Pythagorean's theorem, and it says that even though the boat's speed tops out at 1.85, we're only going to be making our way across the river at 1.41. And so when we find out how much time it's going to take, the distance across is 110 meters, and we're making our way across at 1.41. It's going to take 78 seconds. Okay. Now, what would happen if instead we wanted to get to the other side as fast as possible? We don't care about where we land. Well, what would happen if we just turn the boat and take the boat's velocity and direct it right across the river? Well, what we would do then is direct the boat so all the velocity is used in crossing the river. But what's going to happen meantime then, during that time we're crossing, is the boat will be carried downstream. So we have to realize we're not going to land at a point on the other side. We're going to land somewhere over here, and we can determine where that would be by setting up a different triangle. This time, this is going to be the speed of the boat, 1.85. This is the speed of the water, 1.2. And the net velocity, the boat with respect to the shore, is going to be the hypotenuse. So let's see how these numbers differ. And in this case, we've got a triangle. Let's see, this is the 1.85, those are the two sides of the triangle. So this time we're going to take the tangent. Instead of using the sine function, now we're going to use the tangent to determine how this is working out. This is going to be 1.20, 1.85. That's giving us an angle. So if we direct the boat straight across, then the boat is going to be carried across the river at an angle of 33 degrees. Now, it worked. If we look at the time here, now we're making our way across at 1.85. We get there faster. So we get there in 60 seconds instead of, what was the other one, 74 or something? 78. So we're saving 18 seconds, but we're going to be carried downstream. And we can calculate that distance downstream. It's Vx times t. We're going to be carried 71 meters downstream, so that's a good distance. So you have to decide what we wanted. Oh, that's it. And so we did wrap things up. I think we went over just a bit. So take a look at all of these examples. I feel like the stuff we had set up for today, it's a good set of examples to work from and really think about in these chapters. And then whatever questions come up, stop by office hours and we'll take a look at those.